All right, off we go again. So in this particular video, I want to focus on what is usually referred to as the ambiguous case, where you have an angle side triangle or a side angle. Now that's the one that we avoided back in Math 2 because we kind of knew there was something wrong with it. If you have side angle side, you know that will always define precisely one triangle. There's only one way to have two sides and an included angle matching anything. So as soon as you know that, you can get that. ASA as well. There's all of those different triangle congruence theorems that we learned back in the day. And those all work great. Angle side is just, the two that we can't do is AAA. I always tell my kids, no tow trucks and no donkeys. No tow truck is AAA and an ass is a donkey, right? No tow trucks, no donkeys. Those are the ones that are a little bit worrisome. But we're going to tackle that angle side case right now. So I'm going to go ahead and share this to a really wonderful GeoGebra demonstration that I found. So what you'll notice here is we have a situation where we have an angle and we've got two sides. Now, this is obviously not put together, but you can see that if I could take this and drop this down right here, you could see that I have defined a triangle, haven't I? I've got an angle, I've got a side, I've got another side. And in fact, if I handed this to somebody else, this is the only place I could actually position that thing to make a triangle. And if I position it dead on right there, I've made one triangle. In fact, this is a situation where if I gave an angle side, there was literally one and only one triangle, and therefore it could be considered a triangle congruence theorem. But there's other situations, like let's just imagine that I made this angle a little bit larger, and I made this angle maybe this side here a little bit smaller. I'm hoping this works. I could have, in fact, let me make this one bigger too. That's okay, about like this is going to work. So here's what I've got. I've got angle side again. Now, if I were to swing this across, I could say that I made a triangle right here, couldn't I? But somebody else might have actually brought that across over to here, and there's a totally separate triangle. So there's this clearly obtuse angle down here at the bottom, angle B right here. Or it might be over here, in which case angle B might have been an acute angle. Well, this triangle and this triangle are two valid answers that still have those given angles and two sides. That's why we call it the ambiguous case. This is a situation where, based on the given information, there's actually more than one triangle that can satisfy it. So we sometimes have one triangle. That was the first example that I did. Sometimes we have two triangles, and in fact, there's a third situation where sometimes you have something like this where you try to work on it and there's just flat out no way to make that happen. There's another demo that someone came up with, which is effectively the same demonstration. Why are you not coming up? Let me refresh that. That just basically animated that very same set of ideas. And so you'll notice we have a given angle and two sides, and if this A was that short, it's just not long enough to reach. But notice that if I made that side a little bit longer, eventually it hits to the point where it could swing back and forth, and it could have a larger triangle and a smaller triangle. Notice the triangle involving B2 would be an acute triangle, and the one involving B1 would be an obtuse triangle. And if you do it exactly right, very, very difficult to make it exactly right, but you could imagine where you make that swing just the exact perfect length to where it just touched right there at the base and made precisely one triangle. So what we're going to do is we're going to take a look at a couple of examples on how to handle that particular story. So here we go. Let's take a look at example number, what I'm going to call example number 1. And so in example number 1, I know, and given that the measure of angle A is 26 degrees, that the side length B, move that camera a little bit, but the side length B is 14 inches and the side length A is 11 inches. Now, clearly there's two sides in an angle, but when you first do that, sometimes it's hard to tell if that's side angle side or angle side side or what it is. So I just go ahead and make a quick sketch. I don't really care how good the drawing is, but here is angle A, which is 26 degrees. Side A, 11 inches sitting over here. And we've got, well, side B, I'll go ahead and call this one B, and this is 14 inches. So you can see this is a side-side angle or an angle-angle side. So this is definitely one of those ambiguous cases. So the question is there one, is there zero, or is there two triangles? That's my question. Which one is it? Well, in other words, is this side long enough to reach? If it is, it can't be zero, or is it just the wrong length to where I could swing the side over here and it would land right in here somewhere? So we're going to find out if it is going to be one of these two cases. So we're going to start with this and say that the sine of 26 degrees is to 11 inches as the sine of B or beta. Sometimes I'll use the Greek letters. I'll use alpha, beta, and gamma, but I'm just going to use regular letters today, over 14 inches. Let's go ahead and cross multiply. I get 14 sine of 26 is 11 sine beta, or B. And so that makes the sine of B. I'm going to grab my calculator real quick, and I'm going to type in 14 sines of 26, and let's divide that by 11, and I got 0.557. Now, interestingly enough, my next step is going to be to take the inverse sine. But you want to remember that the inverse sine was only defined in the first and the fourth quadrant. Uh-oh, this is like a bad memory for some of you guys. In other words, if my triangle is somewhere from 0 to 180 degrees, if it's an obtuse angle, the law of sines can't do this. It cannot give me that obtuse angle because it can only give me something from 0 to 90 if it was positive and 0 to negative 90 if it was negative, but that doesn't even exist here in an actual triangle. So let's see what happens when I take the inverse sine. It would be 33 degrees. So the measure of angle B would be 33.912. But you want to remember that there's actually not just one place where the sine could be positive 0.557. There's actually two places where the sine is positive. It'd be here or here, but the law of sines has to be 1 to 1. It can only give me one angle. So I'm going to call it the measure of angle B prime because maybe there's another angle. So the one that has exactly the same reference, here's the big trick. I'm going to take 180 and I'm going to subtract that 33.9 degrees, and I got 146.087 degrees. So if there is a second triangle, then that other angle B would be 146. Now, I don't know if that actually works or not, but we're going to find that out right here. So I'm going to write option 1 and option 2. Let's find out. So I'm going to redraw my figure. I've got a 26 here for A. I've got B was 33.9, at 11 and a 14 over here for option 2. Again, yeah, I know my triangle is a terrible looking triangle for the given information, but I don't really care that much because this is really just a place for me to store my work. And I'm going to call this 146.087. Now that looks terrible to call that 146 degrees, but the question is, can this actually exist? Well, let's see. If I take this and 26 and add them together, and I take that away from 180, 180, take away 26, take away 146.087, I got that this angle is 7.913. So is it possible to have a 7.9 degree angle? Well, that answer is absolutely you can have that. So this not only might have, in fact, it does have two triangles. And I can solve now both of those triangles. Over here, I could say now that the only thing that I don't know is side C down here. So I could say the sine of 7.913 is to C as the sine of 26 is to 11. I could have also said as the sine of 146 is to 14, but I picked this because it was a little easier. I'm not going to take the time to solve that right now because we've already done that. Now let's look at this one over here, option number 1. So in this particular one, let's see, we had 180, we lose 26, and then we lose 33.91, and we're at 120.09 degrees. Now clearly, if this one works, so will this one. So I could again say that the sine of 26 is to 11, as the sine of 120.09 is to little c. So notice we have two totally separate c values that exist there. In fact, I think I'll go ahead and find both of them. So it'd be 11 times the sine of 120.09 divided by the sine of 26. So this c value over here would have been 21.71 approximately. The one over here would be 11 sines of 7.913 divided by the sine of 26. This one would have been a c value of 3.45 inches approximately. So we've got two very distinctly different triangles that could exist. So that's one of the reasons why we could never use this as a triangle congruence theorem, because that would mean that we all have to have the same triangle, and this clearly has two options. Now my second example is going to be a much faster example. So let's check out example 2. Now example 2 basically says we've got the measure of angle C is 82 degrees. We know that the side length of A is 15 centimeters and the side length of C is 7 centimeters. Now again, I just do the same thing every time, little creature of habit thing, ABC, C is 82 degrees. Side length A should be opposite here, and side length C is opposite here, that's 7. So it looks to me like I would want to set up that the sine of 82 over 7 would be equal to the sine of A over 15. I can't use B because I don't know anything about the side or the angle. So what I get is 15 times the sine of 82. I'm going to multiply both sides by 15. Now, something interesting happens this particular time, because when I take 15 times the sine of 82, and then I divide that by 7, I have that the sine of A is 2.122. But we know something. When we graph the sine wave, its maximum value was 1 and its minimal value was negative, when there was no way that a sine wave could ever go higher than the number 1. If you think about it through like old SOHCAHTOA, if the sine is 2, then the ratio of the opposite to the hypotenuse has to be 2. That means the opposite side is twice as big as the hypotenuse, which is physically impossible. So when we talk about does this have 0, 1, or 2 triangles, this one just doesn't even have one. There is no such triangle. That triangle physically cannot exist. That little leg in the swinging identity thing was just flat out too short. Which, by the way, if that is helpful, I will share both of those GeoGebra links to you so you can play with them. Now, our last identity, clearly we've had one where there was no triangle, one where there was 2 triangles. If you guessed at this one, you'd probably be right that I'm going to show you one situation where there's precisely 1 triangle, and that would be the situation where we could have used angle side side as a triangle congruence identity. Okay, so measure of angle B this time is 62. Side length B is going to be 13. And I'm not even going to say what kind. We're just going to call it units this time. And this is 9. So here we go. So here's my A. Here's B. Here is C. So if B is 62 and side length B is 13, side length here is 9, you can still see the angle side plane. So when I go ahead and I take a look at the sine of 62 is to 13 as the sine of, well, let's see, I guess we're going to have to go with C right here. C is going to be to 9. So just like the previous problem, I'm going to multiply both sides by 9. Now, I always assume that there's a secondary triangle. So let's see what happens when I make that assumption. 9 times the sine of 62 divided by 13, I got the sine of C is 0.611. Now, is it possible that the sine could hit 0.6? Well, it's between -1 and +1, so that's an affirmative. So we know we at least have one valid solution. So inverse sine is 37 degrees. So my possible value of C is 37.68 degrees. And I'm going to call this C, measure of angle C. Measure of angle C2, let's call this one C2. 180 minus that would be 142 degrees. Well, so just like that previous one, we're going to go option 1, and we're going to go option 2 over here. And when we look at option 1, just labeling this up real quick, we got 62 degrees here, we have 37.68 right here. Side C is 9, this is a 13. If we have that 37.68 and we take off that 62, we've got 80.32 for the measure of angle A. Now, I have not finished this problem, but if we wanted to find sine A, we could say the sine of 80 is to 8 as the sine of 62 is to 13. That's going to be great. So this is clearly an okay triangle that we can solve. Option 2 over here, however, I've already given you the hint that this isn't going to work, is that when I go to option 2 and I name everything that I know, and I put this other optional measure of angle C in at 142.3 degrees, we have a serious problem because these things already add up to more than 180 degrees. So this triangle cannot exist. So we have exactly one triangle to solve. We would just simply have to finish this one off. So it's pretty easy to tell if there are no triangles, because if there are no triangles, the law of sines just won't work. It'll just blow up when you take your inverse sine. It's actually fairly easy to find out when there is not that second triangle, because when you try to make it, it crashes on you. And so I always assume there is a second triangle until the mathematics tells me that it does not exist. So for this particular set, I would like you to try to do some of the work on law of sines that is laid out in Google Classroom. I hope that was very helpful. Please let me know if you have any questions. It's been great. Thanks. Bye.